All right, this is section 8.4, which is called partial fraction decomposition. I'm going to start with something that may take you all the way back to either elementary or intermediate algebra. It actually may be something you haven't thought of in a while. Let's talk about adding some sort of algebraic fractions like this. Well, as you probably remember, the way to do this is you get a common denominator. The obvious common denominator here would just be the two denominators multiplied together. That is x plus 3 multiplied by x minus 5. So here, I want to have x plus 3 times x minus 5. And here, I want to have x plus 3 times x minus 5. Then the denominators will be the same. We can just add the numerators. Here, I've got the x plus 3. What I need is the x minus 5. I can multiply by x minus 5 in the bottom as long as I also multiply by x minus 5 in the top. Similarly here, I've already got the x minus 5. I need an x plus 3. I can multiply by x plus 3 in the bottom as long as I also multiply by x plus 3 in the top. This is 2x minus 10. This is 3x plus 9. So the final answer will be 2x plus 3x. Negative 10 plus 9 is negative 1. Now, partial fraction decomposition asks you to do exactly what we just did backwards. If we start with something like this, which is not very easy to integrate in this form, can we rewrite it as something over x plus 3 plus something over x minus 5 and easily figure out what these numbers are, and then go ahead and just integrate these terms individually, which turns out to be really easy? And the answer is yes, we can. There's an easy way to do this, and it's called the cover-up method. It's also sometimes called the Heaviside method because one of the guys who really liked using it was an engineer named Oliver Heaviside early in the 20th century. So let's go backwards. If I start with 5x minus 1 over x plus 3 times x minus 5, I know that's something over x plus 3 plus something over x minus 5. How can I figure out these missing numbers? Well, to do it, you use this cover-up method. Here, I ask myself this question. If x plus 3 equals 0, what would x equal? Hopefully the answer is obvious, negative 3. So now what I do is I cover up the x plus 3 term, and I plug negative 3 in everywhere that's left. If I plug negative 3 in here, 5 times negative 3 is negative 15, minus 1 is negative 16. If I plug negative 3 in the bottom, negative 3 minus 5 is negative 8. Negative 16 divided by negative 8 is 2. Notice it works. We can do the same thing here. You look at the bottom term, you say to yourself, what would make x minus 5 equal 0? That would be x equals 5. So now I have to cover up this term, and I plug 5 in everywhere that's left up here. 5 times 5 minus 1 is 25 minus 1, which is 24. 5 plus 3 is 8. 24 divided by 8 is 3. So we now have a really useful technique that can turn a problem like this, which is not so easy to integrate, into two integrals that look like this, which, if it's not obvious to you already, you'll see in a moment are quite easy to integrate. All right, so let's do some examples.